two electrons in two solar systems. We need one photon per electron, four photons. So we get two electrons from water to NADPH, requires four photons. So absorption of four photons leads to synthesis of 4, 3 ATP, or 1 ADPH. Or you can say 3 photons, 1 4 photons, 4 protons, 3 ATP, so 3 photons per ATP. So how much energy is this? How much energy per photon? Well, it turns out that if we take 700 nanometers, which is the max for P700, we're close to max P680. 1 mole of photons. The energy for 1 mole of photons is called an Einstein. What about that? Einstein. And that is equivalent to 170 kilojoules. Again, a mole. So 1 photon's equivalent to the absorption of 170 kilojoules worth of energy. Okay, so how much energy do we need to convert CO2 to glucose? And this is what we'll be dealing with the whole next lecture, so just take it faith for a moment. Requires 12 ATPH to reduce 6 CO2. 18 ATP generate 6 C6 is 12 glucose plus 12 P plus 18 BP plus 18. So 18 ATP is what we need. Generate 1 glucose. So we need 18 ATP. Remember, 3 photons per ATP. So 18 ATP at 3 photons each is equivalent. 3 times 18 is 54. 54 photons at 170 kilojoules. That equals 170 times 54 is line 180. So the amount of energy, this is the amount of light energy absorbed to make 1 mole of glucose. So this is the amount of light energy absorbed to make 1 mole of glucose. So how much energy is there in a mole of glucose? Well, we've seen this before, right? 6 CO2. Generate C6H12O6. That was free energy change is plus 2870. In other words, 9180 kilojoules of light energy was absorbed. 2870 is conserving glucose. So the efficiency meaning energy stored over energy equals 2870 over 9180. 9180. So somewhere around 30 volts. So that 31% of the light energy is absorbed by the photosystems ultimately ends up being conserved in the form of glucose. Okay, now remember this is under standard conditions, normal conditions. Right, so the actual efficiency is probably much higher than that, but calculating it's about 31%. And one other thing I want to mention is the proton motive force. The last thing to mention is the proton motive force, because we're going to come back to this later. So proton motive force, remember, potential difference plus change in pH. And in photosynthesis, potential difference is somewhere around 70 millivolts. And there's about 3 units change in pH under steady state conditions. Remember here, H plus gets pumped in. All right. And ATP is made on the outside and the stroma. And just in contrast, respiration, aerobic respiration, remember, potential was around 180 millivolts. And it was about 1 pH unit. And in that case, H plus was pumped out. Alright. And ATP was made on the inside. Remember, you have zeros on the inside. This is inside the mitochondria. Okay, so we'll come back to that later. Particularly this large pH change. So this large pH change occurs in the stroma where the pH is going to go up dramatically, almost more alkaline. And that has a regulatory effect. Yeah, one. Okay, very quickly, one more mechanism. So I have this up here. One more mechanism of making ATP. One more mechanism of making ATP. You need to know this. Cyclic photophosphorylation. Cyclic photophosphorylation. So what does this mean? Well, what this means is that, remember, in cytochrome BF, we have a cytochrome B, it's actually a B6. Now, B6 can accept electrons from S to SAB. B6 is donated FBS. So FBS does not get electrons. Okay, so FBS AB normally transfers electrons to ferrodoxin, here then ADPH. Ferrodoxin, ADPH. But in this case, we put some back B6. So then it flows through back to photosystem 1. There's a flash of light, back to photosystem 1, flash of light, back to photosystem 1, and each time photons are pumped. Right? You get this cyclic electron transport. Right? So no photosystem 2, no oxygen is involved. No ferrodoxin is reduced. No ADPH. It's just plus light, electron transfer, protons pumped, and ATP. All right, so black and white, electron transfer, protons pumped, ATP. So this is a very efficient way of making ATP, and happens about 5% of the ATP is made this way, this slightly photophosphorylation under standard photosynthetic conditions. All right, so again, you're short-circuiting the system. From FESA B6. Okay, I have one more thing to say. An A is 85 plus, B is 70 plus, C is 50.